Good morning, class. Um, I think I'm just going to get started because even though not everyone is here, I'm just going to get started because I've got a lot of stuff to cover. Hello. Um, so, uh, we have done circular motion. So, just like last year, circular motion goes really well with gravitation because gravity causes things to orbit in a circle. So, we're going to start talking about gravitation. Um, the gravitational force we already know about. Okay, the gravitational force is equal to m times g, where so gravitational force is basically the same thing as the weight force, right? Actually, it is the same thing. So m is the mass of the thing feeling the gravity. Okay. And g is the acceleration due to gravity. Now, when I learned physics, I always just called g the acceleration due to gravity. But apparently nowadays, they are calling it, or just maybe somehow I missed this, and it was always called this, and I just didn't realize it. But another word for the acceleration due to gravity is to call it the gravitational field. Okay? The gravitational field is the exact same thing as the acceleration due to gravity. There's no difference between the two. It's just a synonym for it, okay? That being said, when we talked about the units of acceleration due to gravity, we've always said, it's meters per second squared. But when you are talking about gravitational fields, to kind of emphasize that, you to sort of distinguish it from any regular old acceleration, you use the units newtons per kilogram. Okay? Newtons per kilogram. So 1 Newton per kilogram is exactly the same thing as 1 meter per second squared. So just like we've said that the acceleration due to gravity on Earth is 9.8 meters per second squared, we could also say that the gravitational field on Earth is 9.8 newtons per kilogram. So they're the exact same units. It's just another word for the same thing, just to distinguish it from accelerations that are caused by other things besides gravity. Okay? So, it's called the gravitational field. So the question we want to answer in this lesson is, how can we calculate the gravitational field? How do we calculate the gravitational field? Okay? And so I'm going to teach you, today I'm going to teach you 4 different scenarios in which I might ask you to calculate gravitational field. So the first one is the easiest. It is a single point mass. So when I say a point mass, I mean that the object is so small that its size can be neglected. Okay, so it is just a point. Okay, and if you have a single point mass, so let's say the single point mass is right here, and the point mass has a mass big M, I usually use the Majin M for big M. If you watch Dragon Ball Z, you know Majin Vegeta, Majin Buu, etc. Okay, and so here's the mass. It's a point mass, so I've just drawn it as a dot. And we want to calculate the gravitational field right here at a distance big R away from the point mass. So if you have a single point mass, the gravitational field is given by big G times big M over R squared. Okay? Where big M is the mass of the thing creating the gravitational field. Okay? So, and that kind of depends on perspective. Okay? So if we're talking about, so little m and big M is the thing making the gravitational field that little m is experiencing. So for example, if we were talking about the Earth orbiting the Sun, we would say, you know, big M is the Sun and little m is the Earth. If we were talking about us standing on the surface of the Earth, then little m would be us and big M would be the Earth. If we were talking about us standing on the Moon, then little m would be us and big M would be the Moon. If we were talking about the Sun orbiting the galactic core, then big M would be the mass of the galaxy and little m would be the mass of the Sun. So whatever the meaning of big M and little m changes. If we were talking about the Moon orbiting the Earth, big M would be the Earth, little m would be the Moon. So I hope that makes sense. R is, of course, the distance from the mass where you want to calculate the gravitational field. And we can see that as R gets smaller, the gravitational field gets bigger. Gravity is stronger the closer you are to the thing. Okay? So in particular, if we move away from the Earth, gravity gets weak. The gravity due to the Earth gets weaker. Big G is a constant of nature, okay? And its value is 6.7 times 10 to the negative 11 Newton meters squared per kilogram squared. So gravitational field is not the net force unless gravity is the only force acting on the object, which if we're talking about astronomical bodies, then usually, yeah, that's the case. 6.7 times 10 to the negative 11 Newton meters squared per kilogram. So that's the same no matter what. It's a universal constant. So make sure you understand that big G is not the same thing as little g. So this is called, so the person who came up with this equation was Isaac Newton. And so this is called Newton's law. Newton's law of universal gravitation. Okay? And the reason is that it's universal is that anything that has mass creates a gravitational field. Okay? You create a gravitational field. Your dog creates a gravitational field. Your house creates a gravitational field. Anything that has mass creates a gravitational field. It's universal. It's just that the gravitational field that you create is incredibly weak. All right. So that is the first scenario that I want to talk about. What if we have a spherically symmetric object okay, That is not a point. So, for example, the Earth. The Earth is a spherically symmetric object, or it's approximately close enough to being spherically symmetric. And it's definitely not a point object. And so, how do we handle this? How do we calculate the gravitational field from something that is an extended spherical object? Okay, and to understand this, we have to calculate this, we have to understand the concept of mass below. Okay, so what if you have a planet, and what if you were inside the planet? So you're inside the planet. If you are inside the planet, then the mass below, you completely ignore all the mass that is farther from the center than you. So this mass, whatever the mass of this region is, that is the mass below. Okay? If you get closer to the center, so that you're almost at the center, the mass below gets smaller. Okay? So type it into the chat if you know. What would be the mass below if you were exactly at the center of the planet? I'm going to wait and see if I can get a response. Zero. Very good. Very good. And by the way, if you are outside the surface of the planet, like out here, then the mass below, notice how the mass below would be all the mass sort of within this region. So it's just going to be the mass of the entire planet. Okay. There's a comment that you are the mass below. Well, one thing is, so we always make a separation for the thing that is experiencing the gravitational field and the thing that is creating the gravitational field. So the mass below does not include you. It includes other things besides you that are below you. Okay, so that's why it's zero if you're in the center. Okay, so if you have a spherically symmetric object that is not a point, then you are going to use what is called the shell theorem. Okay. And I'm not going to prove the shell theorem. It uses quite a bit of calculus. So I think if I proved it, I would probably lose most of the class. So I'm not going to spend, and also it would probably take most of the class period. So I'm not going to do that. But if you have already taken calculus and you're up for a challenge, I would encourage you to look up the proof of the shell theorem. And what it says is that the gravitational field of a spherically symmetric object, so I'll say SSO, is equal to big G times the mass, but it's the mass below you, divided by r squared, where r is the distance from the center. Okay? So the difference is, the only difference with the shell theorem is that it might not be the full mass of the object. It's the mass below you. Okay? So this allows us to do things like calculate what is the gravitational field inside a planet. Okay? The gravitational field inside a planet is caused by the mass that is below you. So it's not caused by the full mass of the planet. It's caused by only the mass below. And then the R value you would use is the distance from the center. Okay. So in particular, if you are at the center of a spherically symmetric object, the mass below you is 0, and so the gravitational field is 0. Okay. All right. If you are outside of the planet, the mass below you is the entire mass of the planet, and so it reverts to the formula for a point mass. Okay. So there's a comment. If you dig a 100-foot deep hole, would the gravity be less, more, or the same? It depends. Okay. And here's the thing, because if you dig a hole, you are decreasing the amount of mass below you, but you are getting closer to the center. So it depends on how those two things change, because planets are not uniform density. Okay, so planets are. If you have a planet that had a completely uniform density, then the maximum gravitational field would be on its surface, actually. Okay, but if you have something that has a non-uniform density, then it can be at a different location. So actually, I believe for the Earth, the maximum gravitational field is somewhere in the mantle. And the reason is that the core of the Earth is the highest density part of the Earth. And so when you dig into the Earth, you get closer to the core. So the core is where most of the gravitational field is coming from. And so you get closer to the core, and that increases the gravity. And the crust of the Earth hardly has any mass, so it doesn't. You don't lose that much mass below, but you get closer. So it depends. But that's a good question. Here's a funny thing. What if you had a spherical shell? Okay, so this is a hollow shell. If you're outside of the spherical shell, then this spherical shell behaves just like a point mass. So it behaves exactly like a point mass, because the mass below you is the entire spherical shell. Okay, so that's completely equivalent. But what if you are inside the spherical shell? So here's the spherical shell, and you are inside it. The whole idea of a shell is that for a shell, all the mass is on the outer skin of it, right? So if you're inside a spherical shell, okay, then there's no mass below you anymore. So the gravitational field is going to be 0. And that this is equivalent to just floating in outer space. Okay? So that's really weird. You cross through the shell and gravity becomes 0. I have an idea for a physics problem where someone falls towards a spherical shell. So they go, fall towards the spherical shell. And then once they get to the surface of the spherical shell, a little door opens up. And then they just bounce around the inside of the spherical shell with a constant velocity, right? Because there's no gravity to speed it up or slow it down. That'd be a fun problem to do. Okay. So let's do an example. A planet has a constant density of 5,000 kilograms per cubic meter. Now, as I said, that's not terribly realistic because unless it was a very small planet, but if you have a large planet, the gravity compresses the rocks in the center of the planet, so the density goes up. Okay, so there's a comment about the mass to radius. Yeah, so I mean, it's a calculus problem, right? So it's a calculus problem. So you know, if you wanted to find the maximum, what is the radius of the maximum gravitational field, you would set dg dr equal to 0. Okay. So yeah. Why is there quote no gravity on the International Space Station? I'm not going to answer that. I'll answer it during the Zoom. Ask me that question again during the Zoom room. Okay. But the comment that it doesn't have enough mass, that is more close to accurate because, yeah, the International Space Station just doesn't have enough mass to create a significant gravitational field. And also, even if it did have enough mass, it wouldn't be zero gravity inside because what does the shell theorem apply to? It applies to spherically symmetric objects. And the International Space Station is not a sphere. Okay? All right, a planet has a constant density of 5,000 kilograms per cubic meter and radius 4.1 times 10 to the 6th meters. What is the gravitational field? 0.5 times 10 to the 6th meters below the surface. Okay. So here's the planet. It has a radius of 4.1 times 10 to the 6th. Okay. But we don't want to calculate the gravity at the surface. We're going to calculate the gravity below the surface by 0.5 times 10 to the 6th. So our mass below is not going to be the entire mass of the planet. It's only going to be this amount of mass. So how far are we from the center of the planet? Well, that would be r equals 4.1 minus 0.5 times 10 to the 6th. So the distance from the center is going to be 3.6 times 10 to the 6th meters. Okay? So what is the mass below you? The mass below you would be this entire shaded mass. And to calculate what that mass is, I'm going to use the fact that mass is density times volume. DMV. When I taught physical science, that's how I had them remember density is mass divided by volume. I said DMV. Even though density is typically denoted by the Greek letter rho, but it doesn't matter for them. Okay, so the volume below. Now the volume below is going to be a sphere of radius 3.6 times 10 to the 6th meters. So I have 5,000 times the volume of a sphere of that radius, which is 4/3 pi r cubed. Okay, so that says the mass is 9.8 times 10 to the 23rd kilograms. All right. So now we use the shell theorem, which says that the gravity is big G times the mass below divided by the distance from the center squared. Okay. And so we get 6.7 times 10 to the negative 11 times 9.8 times 10 to the 23rd divided by 3.6 times 10 to the 6th squared. And we get about 5.1 newtons per kilogram. Nice. So the shell theorem is cool. It allows us to find the gravitational field inside a planet. And we did a problem with constant density, but actually you can apply it to planets that do not have a constant density. As long as they remain spherically symmetrical, that's why it's called the shell theorem, because you can imagine a planet of non-uniform density and thinking about it as a bunch of shells, okay, where each shell has its own density and its own thickness. All right. So you could calculate the mass below by just adding up the masses of all the shells beneath you. That's why it's called the shell theorem. So the next scenario that I want to talk about is what if you have multiple point masses? Okay. Multiple point masses. So maybe they're laid out two-dimensionally. We could think about gravitational fields in the solar system, and the gravitational fields are created by all the different planets. So we have multiple point masses all around the solar system. Okay, and those are all creating a gravitational field. So what you want to do is you want to calculate the individual gravitational fields as vectors. Okay, so with ij components. And then you want to add the vectors. One of the things I forgot to point out is that the gravitational field from a point mass always points directly towards the point mass. Okay, so mass creates a gravitational field that points inward towards the center of the point mass. All right. So let's do an example. This example is going to take place in a universe where big G is equal to 1. Okay. And so what I have is a 3, 4, 5 triangle. All right. This distance right here is 4 meters. This distance right here is 3 meters. And this distance right here is 5 meters, because it's a 3, 4, 5 triangle. Okay. And I'm going to call this point right here X. So there's no mass there. It's just a point where I want to calculate the gravitational field. This is a 100 kilogram mass. This is a 50 kilogram mass. So what I want to know is, what is the gravitational field vector at x? Okay. So first, let's calculate the gravitational field at x due to the 50 kilogram object. Well, what you want to do is you want to do gm over r squared times a unit vector which gives the gravitational field a direction. Okay. So if we do the gm, so we have 1, because I'm in a universe where g equals 1, times 50 divided by r squared, so divided by 4 squared, because this 50 kilogram mass is 4 meters away from that, 4 meters away from x. Okay, and now for the direction vector. So this 50 kilogram mass is creating a gravitational field that points in towards it. So in towards this 50 kilogram mass is going to be in that direction. So this is the direction of the gravitational field from the 50 kilogram mass. That's straight down. That's in the negative j direction. So in that case, the direction unit vector was really easy. So simplifying this, 50 over 16, 3.1. So negative 3.1 j hat is the gravitational field due to the 50 kilogram mass. Now let's do the 100 kilogram mass. It's going to be gm over r squared times the direction vector. Okay. So big G is 1. Excellent question. Would these two masses gravitate towards one another? Yes. I'm assuming that they're pinned down in place. But in reality, it's really tough to get a constant gravitational field because the things that are creating the gravitational field are moving around themselves in response. Okay? So there's kind of like, you know, the gravitational field I experience is due to the rest of the universe. The gravitational field that you experience is due to the rest of the universe from your perspective. So that includes me. All right? But you don't experience your own gravitational field. You experience the gravitational field due to everything else. So each individual item in the universe is experiencing the gravitational field due to everything else and moving in response to that. Okay? So this is a 100 kilogram mass. All right? And because it's a 3, 4, 5 triangle, this is 5 meters away, so divided by 5 squared. And now we got to do the direction vector. So this direction vector is a little bit trickier. All right? It points in towards the 100 kilogram mass. So this is the direction of G100. And so when we make a direction unit vector, what we want to first do is get the direction right. And then we make it a unit vector afterwards. So this vector points in the same direction as a vector that goes down 4 and over 3. Okay? So my direction vector is going to be it's going to be proportional to minus 3I hat minus 4J hat, because it goes down 4 and it goes to the left 3. All right? But this isn't a unit vector. So how do we make it a unit vector? We have to divide by its magnitude. The magnitude of this vector, if you work it out, square root of 3 squared plus 4 squared is 5. So I divide it by its magnitude, and that slices it down and makes it a unit vector. Okay? If you have a vector of length 5 and you divide it by 5, it's now going to be a unit vector. It's now going to have a length 1. All right, so my direction vector in this case is minus 0.6 I hat minus 0.8 j hat. Now I can distribute that through, and what I get is G100 equals minus 2.4 I hat minus 3.2 j hat. All right, so now the total gravitational field at point X is going to be equal to the vector sum of these two. So it's going to be negative 3.1 j plus negative 2.4 I hat minus 3.2 j hat. So this is going to be negative 2.4 I hat minus 6.3 j hat. That many newtons per kilogram. I could ask you something like, what is the magnitude of the gravitational field at point X, in which case you would do the Pythagorean theorem on that. All right? So we have one more scenario. It's going to be a 2-pager today. Bug, it's a 2-pager! Bug? All right. So in this case, this is the last case I'm going to teach you about for today, which is, what if you have an extended linear object? Okay? An extended linear object. So here's the scenario that we're going to consider. All right? We have a point, which is the point A, and that point is in front of an extended linear object that has mass. Okay? So this extended object is going to create a gravitational field that pulls the mass A to the right. Okay? So the mass A is at x equals negative 5 meters. The front of the extended linear object is at x equals 0 meters. And the back of the extended linear object is at x equals 7 meters. Okay? And this thing has a non-uniform density. Okay? So it's less dense at the front than it is at the on the front side than it is on the back side. So I hope that represents it kind of. So whenever you have an object with a non-uniform density, you need like an equation for the density, okay? And because this is a linear object, we're going to have what's called a linear mass density. So regular density is mass per volume, but linear mass density is denoted by the Greek letter lambda, and it is mass per length, dm dx. Okay, regular density is dm dv, mass per volume. So the units of linear mass density would be kilograms per meter, because it's mass per length. Okay? And because it's a non-uniform linear mass density, that means that the linear mass density is a function of position. And I'm going to say that it's equal to 4x. All right? So 4x is dm dx. So that means that the linear mass density at x equals 0 is 4 times 0 equals 0. The linear mass density at x equals 7 is 4 times 7, 28 kilograms per meter. All right, so what if you have an extended linear object like this? Here's how you calculate the gravitational field at point A. It's going to be equal to the integral of g times dm over r squared. So dm is the mass at location x. Okay. R is the distance between A and the mass at x. Okay? So, how do we get, and so for the rest of this problem, we're going to assume that we live in a universe where g equals 1. Okay, for the rest of this problem. So how do we get the mass at x? Well, we simply rearrange this formula. Okay, if I have 4x equals dm dx, then by multiplying both sides by dx, you get dm equals 4x dx. So this is what dm means. Okay? Now I have to figure out what is r. R is the distance between a random bit of mass at location x. So let's look at this piece of mass right here. It's at location x and A. All right? And I would like to put forward that r equals x plus 5 in this case. So why is that? Well, how far away is the mass at x equals 0 from A? Because A is at x equals minus 5, this distance right here is 5 meters. Okay? So what if I plug in 0 for x? The mass at location 0 is 5 meters away from A. Perfect. How far is the back end of the extended linear object from point A? Well, it takes 5 minutes to get, or 5 meters to get to x equals 0, and then an additional 7 meters to get all the way to the back side of this linear object. So that's a total distance of 12 meters. So what if we plug in x equals 7, we get 12. You see how that works? So this makes sense. So now what we do is we just plug these two things into the formula. Again, I'm using big G equals 1, so I'm not even going to include it. All right. And so we have dm, which is 4x dx, divided by r squared, which is x plus 5 quantity squared. Now this is a definite integral. So basically what we want to do is we want to integrate over the bounds of this extended object. Okay? So this extended object goes from x equals 0 to x equals 7. So your integral is going to go from 0 to 7. All right? So this integral is your answer. Now, I would expect you to set up this integral exactly how I have. You need to know how to set up the integral. Since some of you are in Calculus AB currently and you haven't learned about integration, to evaluate the integral, I'm going to show you how. All right? And that's going to require me to share my desktop. Okay. So here's my desktop. And I went to a website called Wolfram Alpha, which does it does a lot of stuff automatically, a lot of random stuff. Okay, and so I'm just going to type in what I want to integrate. So I'm going to integrate, and the function was 4x over x plus 5 quantity squared. Okay. This is the function that I want to integrate. And I want to integrate it from x equals 0 to x equals 7. And I just hit enter. So what you should always do is you should always double check that the integral it's doing is the same thing as I had written down. So this right here is exactly the same as what I had written down. So I know that it's interpreting my input correctly. Okay, and I can see that the answer is 1.1685. So let me write that down. Okay, so now I can go back to my webcam. So the gravitational field at point A is 1.17 newtons per kilogram. And obviously it's going to point to the right because this line is going to suck the mass in towards it. All right? So we have learned 4 different scenarios for calculating the gravitational field. We have learned how to calculate it for a point mass. We have learned how to calculate it for a spherically symmetric object. We have learned how to calculate it for multiple point masses. And we have learned how to calculate it for an extended object with a non-constant density. All right? So that is my lesson for today, and I will see you in the